Now we're going to look at the dielectric constant in a little more detail. And as it says here, the definition of the dielectric constant, kappa. So Greek letter kappa is the variable we use to designate the dielectric constant, is defined as a definition by equality, 3 equals sign, to be the electric field in vacuum, so always the electric field in vacuum on top, divided by the electric field of whatever material the E field is traveling through in the problem you're looking at. Typically this is an insulating material, and we'll see why that's true in a moment. Well, let's take a look, as it says here, at the kappa value for vacuum. So the kappa value for vacuum is saying that the material itself is vacuum. So if the material itself is vacuum, then we have the electric field in vacuum always on top, divided by the electric field in vacuum is 1. So please get this into your notes, that the electric field of vacuum is 1, and that 1 will be the smallest possible value for the dielectric constant. We're going to see why in a second. So what if we have a dielectric constant of 2? So this one we've already talked about a little bit, but let's see in terms of our new equality by definition what it means. Well, if the dielectric constant is 2, that means that the material that the electric field is going through must have an electric field value of 1/2 that of the electric field in vacuum, because the electric field in vacuum cancels out, and that's where our 2 comes from. We are always comparing the electric field in a material to the electric field of vacuum. The electric field in vacuum always goes on top. So if we had 1/3 the electric field in vacuum, if that was what the material was doing, that would be a dielectric constant of 3. If we had 1/4 the electric field in vacuum, that would be a kappa value of 4, and so on. And we've already seen this, that if we consider what this does, if we consider the electric field in vacuum as the electric field of these 4 lines, right, streaming in through just air or vacuum, kappa 1. Now they hit the material that we're told has a kappa of 2. Kappa of 2, as we just said, is the electric field in the material is 1/2 that of the electric field in vacuum. So that is why we get just the 2 electric field lines. The spacing is twice as far apart, so the E field is 1/2 as strong. That's exactly what our kappa is showing us. Well, how about for the conductor? We said, well, kappa is really used for insulators and not conductors. Why not? Well, as it shows here, the electric field inside of a conductor is always 0, because you will always get perfect polarization to have an internal electric field, canceling out the external electric field, so you get a net field of 0. So always have electric field of 0 inside of a conductor, which means our kappa explodes and really does not have a definition or meaning. It would be a kappa of infinity. Now, we're going to use kappa more in the course as we go along, but for right now, what we have talked about so far is by far the most important, right? Kappa of 2 means 1/2 the electric field in vacuum. Kappa of 3 means 1/3, and so on. The language we use and how we talk about kappa can be a little tricky, and that's what I have down here. And the most important thing, and really the only thing I need you to focus on at the moment, is that the bigger the kappa value, so as it says here, the bigger the kappa value, the more like a conductor that material is. The bigger the kappa value, you're working your way up to infinity for a conductor, but the bigger the kappa value, the more like a conductor, the more polarization you get, the fewer lines, the fewer field lines in the material. Now, if we think about it, this means that the material more strongly polarizes, right? Like a conductor, the bigger the kappa value. Therefore, kappa is really a measure of an insulator's inefficiency, right? So the more conducting it is, the more inefficient it is as an insulator. And we will certainly be using kappa more in the future, and talking about the insulating properties and how the dielectrics are used in other electrical systems. But for right now, I think this gives us a nice fundamental understanding of the definition of the dielectric constant and will allow us to have further discussion.